Tonight, we're going to journey toward a boundary where even the word before may lose its meaning. Was the Big Bang truly the first moment of everything? Or did cosmic inflation, a contracting universe, a quantum bounce, or a timeless state exist before it? By the end of tonight, you'll understand what science really knows about the origin of the universe and where our equations still fall silent. Before we begin, nearly 90% of viewers haven't subscribed yet. One subscription would help me get closer to 1,000 subscribers, and that would truly mean a lot to me. Thank you. Now, let's begin. When we ask what came before the Big Bang, the question sounds simple only because the word before is so familiar to us, woven into every ordinary experience of memory, cause, and change. Yet in cosmology, that single word becomes the deepest part of the mystery, because before is not merely a direction on a timeline, but a relationship that can exist only if time itself already exists. To understand what the question truly means, we must first separate several ideas that are often blended together in popular language. The Big Bang is not best understood as a bomb exploding into a dark and empty arena with matter rushing outward from one central point. In the standard cosmological picture, space itself was expanding, and every sufficiently distant region was moving away from every other region because the geometry between them was changing. There was no known outer room into which the universe expanded, and no privileged center from which the expansion began. If the cosmos is spatially infinite today, it may also have been spatially infinite in its earliest hot phase, only with distances between neighboring locations compressed to extraordinary smallness. If it is finite, it may still be unbounded, more like the three-dimensional analog of a sphere's surface than a container with walls. The phrase Big Bang therefore refers, in its most secure scientific sense, to the early, hot, dense, rapidly expanding state from which the observable universe evolved, not automatically to an absolute beginning of all reality. This distinction changes the question immediately. If by Big Bang we mean the hot early phase, then asking what came before it is scientifically meaningful, because there may have been an earlier stage such as cosmic inflation, a contracting universe, or a quantum gravitational transition. If by Big Bang we mean the mathematical singularity that appears when classical general relativity is extrapolated backward, then the question becomes more delicate, because a singularity may mark not a physical object or event, but the failure of the theory being used. And if by Big Bang we mean the absolute origin of space, time, matter, energy, and physical law, then we have reached a question for which current science does not yet possess a confirmed answer. The history of modern cosmology quietly mirrors this deepening of meaning. Einstein's general theory of relativity, completed in 1915, replaced the old picture of gravity as a force acting across fixed space, with a description in which matter and energy shape space-time, while space-time guides matter and light. Alexander Friedmann soon found expanding and contracting solutions to Einstein's equations. Georges Lemaitre connected such solutions to astronomical observations, and later, measurements of distant galaxies strengthened the case for cosmic expansion. The discovery of the cosmic microwave background then revealed a faint thermal afterglow from a time when the universe was young, hot, and opaque. Together, These observations established that the cosmos has a thermal history and was once far denser than it is now. But they did not directly show that reality began from nothing. When cosmologists run the equations of general relativity backward, cosmic distances shrink, densities rise, temperatures climb, and curvature can grow without bound. In the simplest classical models, this backward evolution approaches a singular limit. Yet, an infinity in an equation is not automatically an infinity in nature. It may instead be a warning that the mathematical framework has been extended beyond the domain where it can reliably describe the world. Classical physics could not explain the stability or spectra of atoms. Quantum theory did not reveal that atoms were impossible, but that a deeper language was required. In the same spirit, the Big Bang singularity may indicate that general relativity, a classical theory of space-time, must be replaced or completed by a quantum theory of gravity at extreme densities. The more precise mathematical statement behind many singularity results is not that the universe was once a literal point of infinite density floating in nothingness, but that certain paths through space-time cannot be extended indefinitely into the past. Such geodesic incompleteness means the classical description reaches a boundary beyond which it gives no further instructions. A boundary in a theory is not necessarily a boundary in reality. It may be an actual beginning, but it may also be a bridge, a phase transition, or the edge of the concepts the theory assumes. This is why the word before must be handled with care. In Newtonian physics, time is treated as an invisible universal river flowing independently of matter. So imagining an empty duration before the universe seems natural. General relativity removes that background river. Time is part of space-time, inseparable from the geometry that evolves with the contents of the universe. Clocks do not measure an external cosmic substance called time. They measure intervals along paths through space-time, and those intervals depend on motion and gravity. Near a hypothetical beginning of space-time, it may therefore be meaningless to imagine an earlier empty moment waiting for the universe to arrive. The familiar comparison asks what lies north of the North Pole. The question is not answered by naming a hidden place farther north, because north is a direction defined on the surface and ceases to continue in the same way at the pole. Likewise, in some cosmological models, pastward time may reach a boundary where the ordinary distinction between time and space changes, so there is no earlier moment in the classical sense. But this analogy is not a proof that time began at the Big Bang. It describes only one class of possibilities. Other mathematically serious models preserve a meaningful temporal order through the high-density regime, allowing a phase before the hot expansion. To know what we are asking, we must also distinguish physical geometry from the coordinates used to label it. A poorly chosen coordinate system can create artificial edges or infinities where the underlying geometry remains regular. The event horizon of a black hole once appeared singular in certain coordinates, yet better coordinates revealed that the horizon itself need not contain an infinite curvature. Cosmologists, therefore, examine coordinate-independent features, such as curvature invariance and geodesic completeness. Saying that the cosmic scale factor becomes zero in an idealized solution is not by itself a complete physical account of what existed, or whether the solution can continue through a quantum regime. The phrase, "what came before," also hides another ambiguity. It may ask about an earlier event, or it may ask for a deeper explanation. An earlier event could be cosmic inflation, during which space underwent accelerated expansion before the hot plasma formed. But inflation would invite the next question. What established the inflating state? A contracting phase could precede expansion, but one would still ask what determined the contraction and the laws governing its bounce. Even a model with no earlier time would leave open why that timeless boundary condition or quantum state exists rather than another. Causal explanation normally works within time, with one event preceding another, while foundational explanation may describe relations that are not temporal. Whether such an explanation is sufficient is partly philosophical, but the distinction arises directly from the physics. There is also a practical observational boundary to our knowledge. Light does not allow us to see arbitrarily far back, because the early universe was an opaque plasma in which photons scattered repeatedly from charged particles. The cosmic microwave background comes from the later moment, when the plasma cooled enough for electrons and nuclei to combine into neutral atoms and photons could travel freely. Earlier eras must be reconstructed indirectly through nuclear abundances, particle physics, gravitational effects, and possible relic signals such as primordial gravitational waves. As we move closer to the Planck regime, roughly associated in a simple extrapolation with times near 10 to the minus 43 seconds, quantum fluctuations of geometry are expected to become important, and neither general relativity alone nor ordinary quantum field theory on a fixed background is likely to be sufficient. The Planck time should not be imagined as a proven first tick of a universal clock. It is better understood as a scale at which our present theories signal that a new synthesis is required. Thus, the question, what came before the Big Bang, resolves into two sharper scientific questions. First, was there a physical phase before the hot, expanding universe, such as inflation, contraction, or a non-classical quantum state? Second, does time itself extend through the boundary where classical relativity fails, or does time emerge only on our side of that boundary? The first concerns the history of the cosmos. The second concerns the origin and nature of history itself. Science has strong evidence for the hot, early universe, increasingly model-dependent evidence for processes that may have shaped it, and no confirmed description of the ultimate past boundary. The most honest answer is therefore not that nothing existed before the Big Bang, nor that another universe certainly did, but that the meaning of before depends on which layer of the Big Bang we are discussing. Before the hot Big Bang, there may have been a real physical phase. Before the classical singularity, there may have been a quantum regime beyond current theory. Before time itself, however, may not describe a hidden era at all. It may be a sentence whose grammar survives after its physical meaning has quietly dissolved, leaving us at the edge of knowledge, where the universe is not yet telling us what happened earlier, but is asking us whether earlier was ever there. Imagine the universe as a film running backward in perfect silence, every galaxy drawing closer to its neighbors, every wavelength of light shortening, every reservoir of matter warming as the distances between particles steadily contract, and the familiar night sky, with its scattered stars and immense black intervals, gradually surrendering its structure to a younger, denser, more luminous state. We begin in the present, where the observable universe is approximately 13.8 billion years old, and cosmic expansion has carried distant galaxies so far apart that much of the cosmos appears almost empty. Yet this apparent emptiness is only the latest frame in a much longer history written into the geometry of space-time. In general relativity, the large-scale universe is commonly described by the Friedmann-Lemaitre-Robertson-Walker metric, a mathematical form based on the observation that when averaged across sufficiently vast distances, matter is distributed with no preferred direction and no privileged location. The changing scale factor, usually written as A of t, does not represent galaxies flying through a pre-existing container so much as the evolving distance between points carried along with the cosmic flow. And the quantity h equals the time derivative of that scale factor divided by the scale factor itself tells us how quickly this geometry is expanding at a given epoch. Reversing the sign of our journey does not reverse physical time in reality. It simply allows us to infer earlier conditions by solving the equations backward, and as the scale factor decreases, the density of ordinary non-relativistic matter rises approximately as a to the minus third power, because the same particles occupy a smaller volume, while radiation density rises as a to the minus fourth power, because photons become more crowded, and each photon gains energy as its wavelength is compressed. This difference means that although matter dominates much of the later history of cosmic structure, radiation becomes increasingly important as we travel backward, until the universe passes through matter-radiation equality roughly 50,000 years after the beginning of the hot expansion. Before that transition, gravity still acts, but radiation pressure changes the way density fluctuations grow, leaving delicate signatures in the distribution of galaxies and in the temperature pattern of the cosmic microwave background. Continuing backward, we reach a universe without galaxies, without stars, and without any darkness in the ordinary sense, because space is filled by a hot plasma of nuclei, electrons, photons, neutrinos, and dark matter, all interacting within an almost perfectly uniform sea. Around 380,000 years after the hot early phase, the average temperature falls to roughly 3,000 Kelvin, cool enough for electrons to remain bound to protons and helium nuclei for long periods, forming neutral atoms in a process historically called recombination, even though these particles had never previously been combined into stable atoms. As the population of free electrons rapidly decreases, photons cease scattering so frequently and begin to travel across the universe almost unhindered. Those photons have been stretched by cosmic expansion into microwaves and now form the cosmic microwave background, a nearly uniform glow at about 2.7 Kelvin arriving from every direction. Its tiny temperature variations, measured at the level of tens of millionths of a degree, are not random blemishes on an otherwise smooth image, but the fossil record of acoustic motion in the primordial plasma. Gravity attempted to compress over-dense regions. Radiation pressure pushed them outward, and the resulting oscillations created a sequence of peaks in the angular power spectrum whose positions and heights reveal the universe's geometry, matter content, baryon density, and early expansion history. The first peak strongly supports a universe whose large-scale spatial curvature is close to flat, while the relative heights of later peaks help distinguish the gravitational influence of dark matter from the inertia of ordinary baryonic matter. Yet, The microwave background is not a photograph of the Big Bang itself. It is more like the surface of a luminous fog, the earliest electromagnetic boundary through which our telescopes can directly see, and everything before it must be reconstructed through less immediate evidence. Moving farther backward through the opaque plasma, we arrive at the first several minutes, when temperatures were high enough for nuclear reactions to occur throughout the cosmos. Protons and neutrons collided, combined, and separated until expansion and cooling reduced the reaction rates below the rate at which the universe itself was changing. This era of Big Bang nucleosynthesis produced most of the primordial helium-4, along with deuterium, helium-3, and a small abundance of lithium-7. The predicted quantities depend sensitively on the baryon-to-photon ratio and the expansion rate, allowing observations of ancient, chemically simple environments to test conditions that prevailed long before any star existed. The broad agreement between calculated and observed abundances of deuterium and helium is one of the strongest independent supports for the hot Big Bang model, although the persistent mismatch involving primordial lithium remains an unresolved problem that may reflect stellar processing, observational systematics, nuclear physics, or less conventional early universe effects. Before nucleosynthesis, at about 1 second, weak nuclear interactions ceased to maintain equilibrium between neutrons and protons, fixing their approximate ratio before free neutrons began to decay. Around the same era, neutrinos stopped interacting efficiently with the rest of the plasma and began moving freely through space, creating a cosmic neutrino background that should still surround us today at a temperature slightly below 2 Kelvin. Unlike the microwave background, these relic neutrinos emerged when the universe was only seconds old, but their extraordinarily weak interactions make direct detection a profound experimental challenge. Their gravitational influence is nevertheless present in cosmological observations, subtly modifying the expansion rate, the microwave background, and the growth of large-scale structure. As the film continues backward into its first microseconds, familiar nuclear matter dissolves. Protons and neutrons no longer survive as stable composite objects, and the universe becomes a quark-gluon plasma, in which quarks, antiquarks, and gluons move through an intensely interacting medium. Particle accelerators can create tiny droplets of similar matter for fleeting instants, offering a limited laboratory window into conditions that once filled all observable space. Near the quantum chromodynamic transition, occurring at temperatures of roughly 1 trillion Kelvin, quarks become confined into hadrons as the universe cools in the forward direction. In our backward journey, those hadrons melt into their more fundamental constituents. The precise character of this transition depends on density and particle content, and at the low net baryon density relevant to the early universe, current calculations generally describe it as a smooth crossover rather than a sharply discontinuous phase change. Earlier still, the electromagnetic and weak nuclear interactions are expected to merge into a single electroweak description, the Higgs field, whose non-zero vacuum value gives mass to elementary particles such as the W and Z bosons and contributes to the masses of fermions, would occupy a more symmetric high-temperature state. At temperatures above the electroweak scale, distinctions that appear fundamental in the present universe become features of a colder phase, reminding us that the laws visible at low energy may be expressions of a deeper symmetry concealed by cosmic cooling. This region may also be connected to the origin of the imbalance between matter and antimatter. The known universe contains overwhelmingly more matter, yet standard particle processes tend to create matter and antimatter in matched amounts. Any successful explanation of baryogenesis must involve baryon number violation, departures from thermal equilibrium, and violations of charge and parity symmetries in accordance with conditions identified by Andrei Sakharov. But the exact mechanism remains uncertain. Possibilities include electroweak baryogenesis, which would require particle physics beyond the simplest standard model behavior, and leptogenesis, in which an early asymmetry among leptons is partially converted into a baryon asymmetry. Traveling backward beyond energies currently reached by accelerators, the film becomes less a recording and more a sequence reconstructed from theoretical continuity. Grand unified theories suggest that the strong, weak, and electromagnetic interactions may arise from a single high-energy force, but no proton decay or other decisive signal has confirmed a particular unification scheme. Hypothetical magnetic monopoles, cosmic strings, and other relics could have formed during symmetry-breaking transitions, yet their absence or extreme rarity constrains the conditions of these unknown epochs. Somewhere before the conventional hot radiation-dominated phase, many cosmologists place inflation, a period during which the scale factor accelerated dramatically under the influence of a field or effective energy component with nearly constant density. Quantum fluctuations generated during such a phase could have been stretched to astronomical scales, becoming the seeds from which galaxies later formed. The remarkable near-scale invariance and statistical simplicity of primordial fluctuations are compatible with broad classes of inflationary models, but no unique inflaton field, potential, or reheating mechanism has been identified, and alternative scenarios continue to be studied. At the end of inflation, if inflation occurred, its energy would need to transform into particles and radiation through reheating, establishing the hot state traced by later evidence. The temperature and duration of reheating remain uncertain, so even the boundary between inflation and the hot Big Bang is not a single observed frame, but a region constrained indirectly by theory and data. As we push the equations farther backward, energy scales approach those at which quantum effects of gravity can no longer be neglected. General relativity treats space-time as a smooth, geometric continuum, while quantum theory describes matter and fields through probabilities, fluctuations, and operators. Each framework succeeds with extraordinary precision in its proper domain, yet their straightforward combination becomes inadequate when curvature and energy density approach the Planck scale. The Planck time, approximately 10 to the minus 43rd seconds, is not an observed timestamp etched into cosmic history, nor is it established as the universe's first moment. It is constructed from the constants of gravity, quantum mechanics, and relativity, and it marks the approximate scale where the distinction between matter evolving within space-time and space-time itself becoming quantum may cease to be sustainable. Here, the backward-running film reaches its final wall, not because nature has revealed a literal surface blocking our view, but because the language used to reconstruct every preceding frame loses its authority. Beyond that wall, candidate theories offer different continuations: a quantum bounce, a boundary without a classical past, a string-dominated phase, an emergent geometry, or no meaningful temporal continuation at all. Their predictions may eventually be tested through primordial gravitational waves, unusual correlations in the microwave background, relic particles, or patterns in the largest cosmic structures, but no existing observation has selected one final account. What remains before us is therefore not a blank frame labeled creation, but a carefully mapped decline in certainty. We can observe the afterglow of atoms forming, calculate the nuclear reactions of the first minutes, infer the plasma of the first microseconds, and use tested particle physics to approach still earlier energies. Yet with every step, the evidence becomes more indirect and the theoretical dependence more severe. At the farthest limit, the film does not show us a confirmed beginning. It fades into a realm where space-time may have changed its nature, and where the next frame cannot be recovered until physics learns how to describe the quantum architecture of the stage itself. A singularity is often imagined as the first spark of existence, a point smaller than any particle, holding the entire universe in an impossible concentration before space suddenly burst outward. Yet this familiar picture is more dramatic than the mathematics actually allows us to say, because in general relativity, a singularity is not usually a tiny object sitting at the beginning of time, but a sign that the geometric description of space-time can no longer be continued in the ordinary way. To understand whether it was truly the first moment, we must move carefully through the logic that produced it, beginning with Einstein's central insight that gravity is not a force acting inside a rigid cosmic stage, but the curvature of the stage itself. Matter and energy influence geometry through Einstein's field equations, while that geometry determines how planets, photons, and freely falling observers move. When these equations are applied to a universe that is homogeneous and isotropic on the largest scales, the result is a family of expanding or contracting solutions governed by the scale factor, a quantity that describes how the distances between co-moving regions change with cosmic time. If the present expansion is mathematically reversed under the assumptions of classical general relativity, the scale factor decreases, the density rises, and the curvature can increase without limit. In the simplest models, the scale factor reaches zero after a finite amount of proper time, and familiar quantities such as temperature and energy density diverge. It is tempting to call that limit the moment when everything began, but a divergence in a mathematical model does not automatically reveal a physical object with infinite properties. It may instead reveal that a theory built for smooth spacetime has been pushed into a regime where smooth spacetime is no longer the correct language. Physics has encountered similar warnings before. The classical equations of electromagnetism assign an infinite self-energy to an ideal point charge. Yet electrons are successfully described only within quantum field theory, where the meaning of particles, fields, and measured parameters becomes more subtle. The infinite result did not prove that nature literally stores an infinite amount of energy at a geometric point. It showed that the classical idealization had reached the edge of its usefulness. In cosmology, the singularity may play an equally cautionary role, but the case is deeper, because the failing object is not merely a field inside spacetime, but spacetime itself. The modern mathematical definition, therefore, avoids speaking too quickly about an infinitely dense point, and focuses instead on geodesic incompleteness. A geodesic is the natural path followed by a freely moving particle or a ray of light when no non-gravitational force diverts it. Proper time along a time-like geodesic is what an ideal clock carried by an observer would record, while an affine parameter performs a related role for light. If such a path ends after a finite amount of elapsed time, and the spacetime cannot be smoothly extended beyond that endpoint, the geometry is called geodesically incomplete. The path simply stops, not because the traveler reaches a wall that can be touched, but because the theory no longer supplies another point of spacetime through which the traveler may continue. This definition matters because a genuine singularity cannot always be assigned a location within the manifold. It is often not part of spacetime at all. It is the missing boundary where spacetime ceases to provide a complete history. The distinction became clearer through the study of black holes. In the original Schwarzschild coordinates, certain metric components appear to diverge at the event horizon, which once encouraged the idea that the horizon itself might be singular. Later coordinate systems revealed that a freely falling observer can cross the horizon without encountering infinite curvature, while the truly destructive behavior lies deeper, where curvature invariants such as the Kretschmann scalar become unbounded in the classical solution. The horizon divergence was a coordinate singularity, an artifact of the map. The central divergence was a stronger geometric failure. Cosmology demands the same caution. A quantity becoming ill-behaved in one coordinate system does not establish a physical beginning, and even a coordinate-independent divergence must still be interpreted within the limits of the classical theory that produced it. The decisive historical advance came from the singularity theorems developed by Roger Penrose, Stephen Hawking, and others during the 1960s and early 1970s. Earlier conclusions about a cosmic beginning often depended on perfect symmetry, leaving open the possibility that the singularity would disappear in a more realistic, irregular universe. The theorems showed that singular behavior could arise under far broader conditions. Their engine was the Ray-Choudhury equation, which describes how a bundle of neighboring geodesics focuses or spreads as it moves through curved spacetime. Under suitable energy conditions, gravity tends to focus time-like or null trajectories, and once the focusing becomes strong enough, conjugate points form and geodesics may become incomplete. Penrose applied this reasoning to gravitational collapse, while Hawking adapted related methods to cosmology, showing that an expanding universe satisfying particular geometric and energy assumptions could not be extended indefinitely into the past. These results were powerful precisely because they did not require the universe to be perfectly smooth. Yet they did not demonstrate that everything emerged from a literal point, or that no earlier non-classical phase could exist. Their conclusion was narrower and more rigorous. Within the framework of classical spacetime, under specified assumptions, the past history is incomplete. Those assumptions deserve attention because the physical universe may not satisfy them at all energies. Traditional singularity theorems often use energy conditions that restrict how stress and energy behave, but quantum fields can violate some of these conditions locally, as occurs in phenomena related to negative energy densities and vacuum effects. Cosmic inflation also involves an effective form of stress energy with unusual pressure, altering which theorem applies and how. Later work, including the Borde-Guth-Vilenkin theorem, approached past incompleteness through the average expansion rate rather than through Einstein's equations and classical energy conditions. In simplified terms, if the expansion measured along certain past-directed paths remains positive on average, those paths cannot be extended arbitrarily far into the past. This places an important limit on many eternally inflating scenarios, but it still does not prove creation from nothing, because an incomplete inflating region may be preceded by a contracting phase, a quantum boundary, a static regime, or some structure not described by classical spacetime. Geodesic incompleteness tells us that one chapter cannot be extended using its own rules. It does not reveal what kind of chapter, if any, lies before it. There is another subtlety hidden in the phrase, first moment. A moment is already a feature of temporal geometry, a slice or event ordered relative to other events. If classical time itself emerges only after a quantum gravitational transition, then speaking of the first classical moment may be meaningful even when asking what happened earlier is not. One can imagine a smooth surface with a pole. The pole is the beginning of one family of directions without being an edge surrounded by empty territory. Some quantum cosmological proposals use an analogous idea, replacing the sharp initial boundary with a region in which the distinction between time and space changes character. Other approaches preserve a temporal sequence and replace the singularity with a bounce, allowing a contracting universe to pass through a maximum density and begin expanding. Loop quantum cosmology, for example, modifies the effective gravitational dynamics in highly symmetric models so that quantum geometry produces repulsive behavior near the Planck scale. In these models, the classical singularity can be replaced by a transition connecting a pre-bounce contraction to the expansion we observe. String-inspired cosmologies offer different possibilities, including phases governed by extended objects, dualities, or additional dimensions. None of these proposals has yet been confirmed as the unique description of the early universe, and results obtained in simplified models do not automatically survive every inhomogeneity, anisotropy, or quantum correction present in a complete theory. Still, their existence demonstrates an essential logical point. The singularity of classical general relativity is not the only mathematically imaginable ending to the backward journey. Even the concept of density becomes uncertain near the supposed beginning. Density is energy divided by spatial volume. But at the Planck scale, the notion of a smooth spatial region may lose operational meaning. Quantum uncertainty may affect geometry itself, so the volume used in the calculation may no longer possess a sharply defined value. Asking whether density was literally infinite could then resemble asking for the precise temperature of a single classical trajectory before the concept of temperature has emerged from statistical behavior. The classical question may be well-formed at late times and ill-formed at the deepest level. Semi-classical gravity, which treats matter quantum mechanically while retaining a classical space-time, can explore part of this territory, but it is unlikely to be adequate when fluctuations of geometry become large. A complete theory would need to explain not merely what fields do on space-time, but what space-time is when it participates in quantum superposition, entanglement, and uncertainty. Until such a framework is both mathematically complete and experimentally supported, the singularity remains a boundary of established explanation rather than an observed event. No telescope has seen it, no detector has recorded it, and no surviving signal has yet forced every viable model to include it as a literal beginning. What observations do support is a universe that was once extremely hot, dense, and rapidly expanding, with primordial conditions that successfully account for the cosmic microwave background, the abundance of light elements, and the later growth of structure. These achievements carry us astonishingly close to the early universe, but they do not carry us through the domain where gravity must become quantum. The most careful answer is therefore that the singularity may represent the first moment of classical cosmic time, but science has not established that it was the first moment of all reality. It could be a genuine boundary beyond which there is no earlier physical time, or it could be the mathematical shadow of a transition that present equations cannot resolve. As we follow the geometry backward, the stars vanish, atoms dissolve, familiar forces merge, and the very fabric used to measure distance and duration begins to tremble beneath the weight of its own equations. At the end of that quiet descent, we do not find a confirmed point where everything was born. We find a place where one of humanity's greatest theories falls silent, and where the silence may conceal a beginning, a passage, or an entirely different meaning of time. There is a quiet but decisive shift in meaning hidden inside the phrase, "before the Big Bang," because the hot Big Bang and the beginning of everything are not necessarily the same event, and cosmic inflation occupies precisely that narrow, uncertain interval between what the universe securely remembers and what our theories can only reconstruct. If the early cosmos passed through inflation, then before the familiar furnace of particles, radiation, and nuclear reactions, there was a state that was not primarily hot at all, but almost empty of ordinary matter and dominated by an energy component whose pressure was sufficiently negative to drive accelerated expansion. In general relativity, acceleration occurs when energy density plus 3 times the pressure becomes negative, or when the equation of state parameter W falls below -1/3. This does not mean gravity simply turned off. Pressure gravitates as well as energy density, and a nearly constant vacuum-like energy changes space-time so that the scale factor can grow almost exponentially. During this interval, physical distances could increase enormously while the local speed of light remained unchanged, because no object needed to race through space faster than light. The geometry of space itself was stretching. The idea arose from a specific historical difficulty. By the late 1970s, the hot Big Bang model had become remarkably successful at explaining cosmic expansion, the microwave background, and primordial light elements. Yet its earliest conditions seemed strangely arranged. Regions on opposite sides of the observable sky possess nearly identical temperatures, even though, in a simple, non-inflationary extrapolation, they appear never to have exchanged light or any causal signal before the microwave background was released. This became the horizon problem. Large-scale geometry also appears extremely close to spatial flatness, although in an ordinary decelerating universe, even a tiny early departure from flatness tends to grow, implying unusually precise initial conditions. Grand unified theories introduced another concern by predicting heavy relics such as magnetic monopoles that should have been produced in abundance but have not been observed. In 1981, Alan Guth proposed that a brief interval of accelerated expansion could address these puzzles together. A small region once in causal contact could be stretched beyond the observable universe. Spatial curvature could be diluted until a curved cosmos appeared locally almost flat, and unwanted relics could be scattered until their density became negligible. Guth's original version, now called old inflation, relied on a metastable false vacuum that decayed by forming bubbles of a lower energy phase, but those bubbles did not merge smoothly enough to produce the homogeneous universe we observe, a difficulty known as the graceful exit problem. New inflation and later slow roll models altered the picture by allowing a scalar field to move gradually along a sufficiently flat potential, so inflation could end more uniformly. In these models, the field, conventionally called the inflaton, is not known to be any particle already identified in nature. Its nearly uniform potential energy acts approximately like a temporary cosmological constant, while the field's motion slowly changes the expansion rate. The slow roll conditions require the slope and curvature of the potential to be small in suitable dimensionless units, keeping the field's kinetic energy subdominant and allowing inflation to last long enough. Duration is often measured not in seconds, but in e-folds, with one e-fold increasing the scale factor by a factor of e. Roughly 50 to 60 E-folds are commonly associated with scales visible today, though the number depends on the inflationary energy scale and the poorly known history of reheating. What inflation truly changes is the behavior of the co-moving Hubble radius, the Hubble radius divided by the scale factor. In a decelerating universe, this quantity grows, but during inflation, it shrinks, allowing quantum fluctuations that begin on microscopic scales to be carried beyond the Hubble radius and preserved as nearly frozen patterns in space-time curvature. This is where inflation becomes more than a remedy for initial condition puzzles and begins to offer an account of cosmic structure. A quantum field cannot remain perfectly still and uniform. It fluctuates, and accelerated expansion stretches those fluctuations to astronomical distances. After inflation ends and the co-moving Hubble radius begins growing again, the modes re-enter. First, as tiny variations in density and gravitational potential. Later, as the seeds of galaxies, clusters, and the immense filaments of the cosmic web. The predicted scalar spectrum is not perfectly scale invariant, but can possess a slight tilt, reflecting the slow evolution of the inflationary background. Measurements of the cosmic microwave background find a scalar spectral index near 0.965 rather than exactly 1, broadly consistent with many slow-roll models. While the observed perturbations are predominantly adiabatic and close to Gaussian. These agreements are important, yet they do not identify a unique model, because many different potentials, multiple field systems, modified gravity theories, and some non-inflationary scenarios can reproduce similar statistics. Inflation also predicts tensor fluctuations, ripples in space-time that could form a primordial gravitational wave background and imprint a distinctive B-mode pattern in microwave background polarization. No primordial tensor signal has yet been securely detected, and bicep/Keck analyses constrain the tensor-to-scalar ratio at a representative pivot scale to less than about 0.036 at 95% confidence. This pressures some simple high-energy models, while leaving many lower-scale possibilities viable. It does not disprove inflation, because viable models can produce a tensor amplitude far below present sensitivity. Nor does the success of a nearly scale-invariant spectrum by itself prove that the fluctuations were quantum in origin, since carefully constructed classical stochastic alternatives can imitate some measured correlations, although inflation provides a well-developed quantum framework linking their shapes and amplitudes to the background dynamics. The transition out of inflation is equally essential, because an inflating universe dominated by smooth potential energy contains neither the hot thermal bath nor the diverse particles required for later cosmic history. As the inflaton approaches the minimum of its potential, its coherent energy may be transferred into other fields through decay, resonant particle production, or more complicated non-equilibrium processes. This interval is called reheating, though it may include an earlier explosive stage known as preheating, and its end establishes a radiation-dominated plasma with a definable temperature. The hot Big Bang, in this more precise account, begins during or after this conversion. Inflation is therefore not the explosion itself. It is a candidate prologue whose fading energy lights the cosmic furnace. Reheating remains poorly constrained, and its duration and effective equation of state influence how inflationary predictions are mapped onto scales observed today. So uncertainty in this hidden interval feeds directly into attempts to reconstruct the inflaton potential. Even if inflation and reheating were eventually confirmed in detail, however, the original question would only move one step backward. What placed the inflaton in the required part of its potential? Why was a sufficiently smooth patch available? Did inflation begin after contraction, emerge from a quantum process, or continue through a larger spacetime? In some potentials, quantum fluctuations can displace the inflaton upward as rapidly as classical motion carries it downward, producing eternal inflation, in which inflation ends locally but continues elsewhere, generating many reheated regions, sometimes described as pocket universes. This is a mathematical possibility within certain models, not an observed cosmic geography, and it creates difficult probability problems when events may occur without finite measure. More importantly, future eternal inflation does not automatically remove the need for a past boundary. The Bohr-Guth-Vilenkin result shows that spacetimes with positive average expansion along particular past-directed trajectories are geodesically incomplete in that direction. So the inflating description alone generally cannot be extended without limit. The theorem does not reveal what replaces the missing past, and does not prove creation from absolute nothing, a quantum boundary, contracting epoch, emergent phase, or physics outside classical spacetime may still provide a continuation. Inflation also raises a trans-Planckian concern. If it lasted far longer than the minimum required duration, some modes now observed across the sky may trace backward to wavelengths smaller than the Planck length, where ordinary quantum field theory on smooth spacetime may be unreliable. Whether unknown high-energy physics left measurable traces depends on the initial state and on how thoroughly inflation erased earlier information. That erasure is both inflation's strength and its deepest limitation. By stretching curvature, relics, and irregularities beyond the observable horizon, inflation can explain why our region looks simple, yet the same process may conceal the conditions from which inflation arose. Alternative frameworks, including bouncing and ekpyrotic cosmologies, attempt to solve some of the same puzzles through different evolution of the cosmic horizon. So the scientific question is not whether inflation is elegant, but which mechanism nature actually used. The careful answer is that inflation may have occurred before the hot Big Bang, and may have prepared the universe for everything that followed, turning microscopic fluctuations into the architecture of galaxies, and transforming stored field energy into the first thermal ocean. Yet it has not been established as the first state of reality. It is a possible room before the fire, not necessarily the entrance to the house, and when we step quietly beyond its accelerating geometry, the darkness ahead remains filled not with a confirmed beginning, but with the unresolved question of what allowed inflation to begin. Perhaps the strangest answer to the question of what came before the Big Bang is that there may never have been a before at all. Not because an empty eternity passed unnoticed, and not because the universe emerged after an immeasurably long silence, but because silence, waiting, and duration are already temporal ideas, and time itself may belong to the universe rather than to any larger stage surrounding it. Our instincts resist this possibility because every ordinary event appears embedded within a sequence, and even the oldest star seems to stand downstream from some earlier condition. Yet general relativity quietly removes the universal clock that common sense assumes. Time is not an invisible river flowing independently behind matter. It is one direction within a dynamical spacetime whose geometry responds to energy, pressure, and motion. A clock measures the length of its own path through that geometry. So asking what a clock would have recorded before space-time existed may be asking the instrument to operate before the conditions defining an instrument, a path, or an interval were present. This idea becomes mathematically serious in quantum cosmology, where the whole universe is treated not as a system evolving inside an external laboratory, but as the system that contains every possible laboratory. Ordinary quantum mechanics presumes a time parameter against which a wave function changes, while general relativity makes time part of the gravitational field, and combining them produces the problem of time. The theory cannot simply borrow an outside clock, because, by definition, there is nothing outside the universe whose ticking could organize its history. In canonical approaches, this tension appears in the Wheeler-DeWitt equation, whose schematic form sets a Hamiltonian constraint acting on the wave function of the universe equal to 0. Unlike the Schrödinger equation, it contains no ordinary external time parameter, so what we experience as evolution may have to emerge from correlations among internal variables, with one degree of freedom behaving as a clock relative to another. The absence of external time does not prove that cosmic time had a beginning, but it makes the phrase "before the universe" far less automatic than it appears. One of the most influential attempts to turn this insight into a concrete model is the no-boundary proposal associated with James Hartle and Stephen Hawking. Instead of imposing an initial condition on a sharp first slice of classical spacetime, the proposal seeks a quantum state by summing, in a path integral description, over compact geometries and regular matter configurations that possess no separate boundary in the past. In this picture, the universe can be finite and self-contained without beginning at a jagged edge, much as the surface of Earth is finite in area but does not terminate at the North Pole. The analogy is only intuitive, because the actual construction involves four-dimensional geometries, complex saddle points, and a wave function over possible three-dimensional configurations. Yet it captures the essential change. Near the place where classical cosmology would expect a beginning, the geometry may close smoothly rather than continue toward an earlier Lorentzian time. The familiar distinction between one temporal direction and three spatial directions can become blurred in the SSL calculation, with an approximately Euclidean region connecting to an expanding Lorentzian universe. Calling this a transformation of time into space is useful imagery, but not a literal movie of a coordinate rotating before an observer's eyes, because no classical observer stands outside the transition. The no-boundary proposal is better understood as a rule for assigning amplitudes to complete possible histories, from which some may become sufficiently classical at larger size to contain clocks, records, and observers who remember a lower entropy past. Modern reviews emphasize that it is a proposal for the wave function and initial conditions of the universe, not an experimentally established account of creation. And its detailed predictions depend on how the gravitational path integral is defined, which saddle points contribute, how perturbations are treated, and how probabilities are interpreted. The difficulty is serious because the Euclidean gravitational action is not bounded below in a straightforward way, making a naive sum over geometries divergent, while newer contour methods attempt to specify which semilsequital histories legitimately contribute. Different implementations have produced debates over whether the proposal favors enough inflation, whether fluctuations remain controlled, and whether observationally acceptable universes receive substantial probability. These disputes show that replacing a singular beginning with a smooth quantum boundary requires more than analogy. A related but distinct idea is the tunneling proposal, developed by Alexander Vilenkin and others, in which the wave function is selected by outgoing wave conditions in superspace, the abstract configuration space of possible geometries and fields. In simplified closed universe models, the scale factor behaves somewhat like a quantum coordinate separated from an expanding classical region by a potential barrier, and the universe is described as tunneling into an expanding state. The phrase "from nothing" can be dangerously misleading. Nothing does not mean a black vacuum, because a vacuum is already a state of fields within space-time. It does not mean an empty chamber, because chambers have geometry. And it does not mean an earlier instant containing no matter, because an instant is already part of time. In the technical proposal, nothing refers more narrowly to the absence of a classical space-time geometry, often represented by a vanishing scale factor at the boundary of a simplified mini-superspace model. Vilenkin and Yamada have shown how tunneling boundary conditions, Lorentzian path integrals, and a limiting picture of a universe of vanishing size can yield related wave functions in particular session settings, but such results remain model-dependent rather than direct observations of cosmic birth. Quantum tunneling itself tempts us to imagine an event unfolding through hidden time, like a particle waiting on one side of a barrier and later appearing on the other. Yet in cosmology, the entire temporal geometry is part of what the wave function describes. The tunneling metaphor therefore expresses a relation between quantum configurations, not necessarily a process witnessed from an earlier temporal platform. This distinction reaches the philosophical heart of the question. If there is no earlier time, can the universe still have a cause? A cause in the ordinary physical sense is an event located earlier than its effect, so a timeless origin cannot possess that kind of cause without contradiction. It may still have a non-temporal explanation through a boundary condition, a quantum law, a consistency principle, or a deeper mathematical structure. But such an explanation would relate the universe to its foundation rather than to a previous event. Quantum cosmology attempts to bring the boundary condition itself into physics, but it has not yet explained why one law, one measure, or one wave function should be fundamental instead of another. Saying there was no before, therefore, does not close every question. It changes the shape of the questions that remain. It removes the demand for an earlier cosmic scene, while leaving open why a timeless quantum state should yield a classical universe with particular fields, constants, dimensions, and unusually low initial gravitational entropy. It also leaves the arrow of time to be explained. A universe without a past boundary may still require a special region in configuration space from which entropy increases, because the equations governing microscopic physics are largely indifferent to the direction we call future. Some no-boundary histories can develop arrows of time away from a region of small size, while other approaches treat decoherence, stable correlations, and coarse-grained entropy as the processes through which temporal direction becomes physically meaningful. None of this implies that consciousness creates time. Macroscopic clocks and memories may simply become possible only after quantum degrees of freedom settle into stable, semiclassical relationships. Another cities that timely create time is the going to the many more with other classical relationships and continues to the contrast of decoherent. Another city is the most of closed quanta consequence before better outload from temporal of any classical relationships. Another feeling field which may simply easily complete, another not worked be included. Another teps that consciousness create time and layer as a company is an only simple and exist. A lot of time with thing that they explains consciousness relationship of this case. Macroscopic clocks and memories may simply become possible only addition time of then explained into the minute. Marcus relationships. The pole is not preceded by another point farther north, although we visualize the surface from an external dimension. The know-before possibility does not require the universe to be embedded in an outside time, and adding such a stage would merely restore a larger timeline in which the question could be asked again. Nor does the proposal claim that absolute nothingness existed and then changed, because change already requires time. It suggests instead that the earliest valid description may be a complete quantum geometry in which classical ordering has not yet emerged. Whether nature chose such a description remains unknown. A future theory may show that time continues through a bounce, that contraction preceded expansion, or that a deeper non-geometric structure supports an ordering unlike ordinary time. Observations of primordial fluctuations, spatial curvature, gravitational waves, and the statistical texture of the cosmic microwave background may constrain particular no-boundary or tunneling realizations, but no measurement has yet demonstrated that temporal language ends at the Big Bang. The scientific strength of this possibility lies not in certainty, but in logical economy. If time is part of the universe's physical structure, then the universe need not wait inside a larger time before existing. At the quietest limit of the idea, there was no darkness before light, because darkness requires a space in which light is absent. There was no silence before motion, because silence requires duration. There was no empty age before the first age, because an age is already measured by change. There may have been only a quantum condition from which the distinction between earlier and later became classical, and from within that later world we look backward until our concept of before reaches its own boundary, not finding a hidden moment beyond it, but discovering that the road itself may begin where the question ends. If the Big Bang was not the first moment, then one of the most compelling possibilities is that the universe did not emerge from a mathematical edge at all, but passed through an interval of extreme compression in which the classical collapse of spacetime was halted and reversed by quantum geometry. In that picture, the hot, expanding cosmos is the far side of a bounce. Before it, distances were shrinking rather than growing. Matter and radiation were being compressed, and the Hubble parameter, positive in our expanding universe, was negative. The reversal would not resemble a galaxy-sized object striking a floor and rebounding inside an external room, because there is no outside surface and no surrounding space. It would be a change in the evolution of the cosmic scale factor itself, from decreasing to increasing, while the geometry, carrying every particle and field, passed through a smallest, non-zero volume. Classical general relativity does not normally permit this gentle turn for ordinary matter in a spatially flat universe. The Friedmann equation makes the square of the expansion rate proportional to the energy density, and the Ray-Choudhury equation shows that matter satisfying familiar energy conditions tends to focus geodesics, driving contraction toward a singularity. A non-singular bounce, therefore, requires some alteration near the highest densities, unusual stress energy, modified gravity, or a quantum description in which the continuum equations no longer remain exact. Loop quantum cosmology offers one mathematically developed realization of the third root. It is a symmetry-reduced application of ideas from loop quantum gravity, where geometry is quantized through variables related to connections and areas, rather than treated as an infinitely divisible classical background. In the simplest homogeneous isotropic model, the smooth scale factor is replaced at the fundamental level by quantum states of geometry, and the differential evolution familiar from the Wheeler-DeWitt approach becomes a difference equation in a volume-like variable. The important consequence is not merely that space is divided into little cubes, an image that is too literal, but that curvature is represented through finite holonomies and acquires bounded behavior in regimes where the classical curvature would diverge. For Simons states, the resulting dynamics can often be summarized by an effective Friedmann equation of the form h squared equals 8 pi g over 3 times rho multiplied by 1 minus rho over rho critical. At low density, the correction is negligible, and Einstein's equation returns. As rho approaches the critical density, the extra factor decreases, the magnitude of the contraction rate falls, and when rho reaches rho critical, h becomes 0, even though the universe has not become empty. The scale factor reaches a minimum, after which h changes sign and expansion begins. In the standard improved dynamics model with a massless scalar field, the maximum density is about 0.41 times the Planck density, and detailed quantum evolution replaces the classical singularity with a deterministic bounce within that highly idealized setting. The scalar field can serve as an internal clock, allowing the quantum state to be followed through the Planck regime without appealing to a time outside the universe. This mechanism is sometimes described as repulsive gravity, but that phrase must be used carefully. No new force necessarily pushes matter outward in the ordinary sense. The effective repulsion arises because quantum geometric corrections change the relationship between density, curvature, and expansion. Far from the bounce, space-time behaves classically, and gravity remains attractive. Near the critical regime, the modified dynamics prevent density and curvature from continuing along the classical divergent path. The bounce is therefore not an arbitrary patch placed over the singularity. Within these models, it follows from the chosen quantization of the gravitational phase space. Yet the result is strongest in reduced cosmological systems, where almost all spatial complexity has been removed before quantization. The actual universe is not exactly homogeneous. It contains perturbations, gravitational waves, possible anisotropies, and perhaps degrees of freedom not captured by a single scalar field. Extending the bounce from a controlled mini-superspace model to a complete quantum spacetime remains one of the central challenges, and different regularizations or quantization choices can alter the critical scale and detailed evolution. The relation between loop quantum cosmology and the full theory of loop quantum gravity is active rather than settled, while some effective formulations raise additional questions about signature change and whether ordinary time remains well defined throughout the highest density interval. If a contracting universe really existed before the bounce, it would also need to arrive at the transition in a sufficiently smooth condition. Contraction does not simply run expansion backward like a perfectly reversible film. Shear associated with anisotropy typically grows as the inverse sixth power of the scale factor, faster than ordinary matter and radiation. So even tiny directional differences can come to dominate as the universe shrinks. This is related to the Belinsky-Kalatnikov-Lifshitz instability, in which the approach to a classical singularity can become highly anisotropic and oscillatory. A successful bouncing scenario must suppress, dilute, or dynamically control this growth. An ekpyrotic phase, driven by a field with an equation of state much stiffer than ordinary matter, is one proposed mechanism because its energy density can increase faster than the shear and smooth the universe during slow contraction. Loop quantum corrections can bound some quantities near the bounce, but they do not, by themselves, erase every question about how realistic initial irregularities evolve across a long contracting era. The origin of cosmic structure creates another demanding test. In the inflationary account, quantum fluctuations are stretched during accelerated expansion. In a matter bounce scenario, nearly scale-invariant curvature perturbations may instead arise during a matter-dominated contraction, when modes leave the shrinking effective horizon before passing through the bounce. Other versions combine a quantum bounce with a later period of inflation, allowing the bounce to remove the singularity while inflation performs much of the smoothing and perturbation generation. The equations describing fluctuations become delicate near Planck density because there is no single, universally accepted prescription for perturbations on a quantum background. Approaches known as dressed metric, hybrid, and deformed algebra frameworks agree in some regimes and differ in others, particularly near the bounce. Depending on the model and the assumed initial quantum state, possible signatures include reduced power on the largest angular scales, oscillatory features in the primordial spectrum, modified non-Gaussian correlations, or changes in the tensor-to-scalar ratio. These are possible discriminants, not detections. Current microwave background observations contain large-scale anomalies of limited statistical significance, but none has uniquely selected loop quantum cosmology over inflationary initial conditions, astrophysical effects, cosmic variance, or other early universe mechanisms. The trans-Planckian issue also remains. Some perturbation modes may possess physical wavelengths below the scale where the effective description is trustworthy, making predictions sensitive to unknown ultraviolet physics. A bounce also does not automatically imply an endlessly cyclic universe. One transition could connect a single contracting branch to our expanding branch, with no repeated return. Cyclic behavior requires an additional mechanism that eventually stops expansion and initiates another contraction, as well as a consistent account of entropy, black holes, particle production, and the accumulation of perturbations from one cycle to the next. Even for a single bounce, entropy gives the arrow of time a subtle shape. If entropy increased throughout the pre-bounce contraction toward the bounce and continued increasing afterward, observers on both sides might not describe the same event as lying in their future. Alternatively, special low-entropy boundary conditions could place the thermodynamic arrow away from the bounce in both directions. The gravitational equations alone do not determine which interpretation nature chooses. The quantum state and its boundary conditions matter. Nor does replacing the singularity answer why the pre-bounce universe existed, how long it contracted, or whether its past extends without limit. The bounce solves a local problem at extreme density by continuing the history through a region where classical relativity fails. but it does not necessarily solve the global problem of origin. The earlier branch might itself emerge from another transition, approach an asymptotic state, belong to a longer cycle, or encounter a different boundary in the remote past. This is why the quantum bounce should be treated neither as fantasy nor as established history. It is a coherent possibility, showing that a singular beginning is not forced once geometry is allowed to become quantum, and in simplified models, it can be calculated with unusual precision. Yet, its connection to the full universe and to observation remains incomplete. If this possibility is correct, then what came before the Big Bang was not nothing, and not an undefined instant, but a real cosmic phase in which space was contracting, wavelengths were shortening, and density was rising toward a finite maximum. Near that maximum, the continuum image would have ceased to be exact. Quantum geometry would have altered the gravitational dynamics, and the inward motion of the universe would have slowed to a moment without expansion or contraction before turning outward. No observer could hover outside to watch the reversal, and no flash would need to announce it. The entire stage would simply change the direction of its evolution, carrying the information of an older cosmos through a narrow quantum passage into the hot, expanding world from which stars, planets, and quiet minds beneath the night sky would eventually emerge. There is a haunting possibility that the Big Bang was not the birth of everything, but the final breath of an older cosmos, a moment when one vast era ended so completely that its death became indistinguishable from the beginning of our own. In a cyclic picture, the universe is not a single story with one opening page and one final period. It is a sequence of cosmic ages, each passing through expansion, transformation, contraction, or some subtler form of renewal, with every Big Bang acting less like creation from nothing than a narrow bridge between worlds. The idea is ancient in spirit, but its scientific form emerged only after general relativity made the geometry of the universe dynamic. Alexander Friedmann's equations allowed space to expand or contract, and in the early 20th century, Richard Tolman explored whether a closed relativistic universe could oscillate repeatedly between a Big Bang and a Big Crunch. Thermodynamics, however, disturbed this elegant symmetry. Real processes generate entropy, and if entropy increases from one cycle to the next, each new expansion should contain more radiation and last longer than the one before it. Running the sequence backward would then produce progressively smaller cycles, suggesting that the oscillations could not remain identical through an infinite past. The old cyclic universe was therefore not a perfect cosmic clock returning forever to the same position, but a system burdened by the irreversible accumulation of history. Modern cyclic theories do not simply revive that model. They alter the mechanism of renewal and, in some versions, replace a violent collapse of all space with a long, extraordinarily slow contraction known as the ekpyrotic phase. The name comes from an ancient Greek word associated with a world-consuming fire. Yet the physical process is almost the opposite of an uncontrolled inferno. During ekpyrotic contraction, the scale factor decreases modestly, while the Hubble radius and characteristic curvature scale change dramatically. The dominant component has an equation of state parameter W, defined as pressure divided by energy density, much greater than 1. Its energy density grows so rapidly during contraction that it can outpace spatial curvature, ordinary matter, radiation, and the shear associated with anisotropy. This matters because contraction is normally unstable. Small directional differences can grow faster than familiar forms of energy and drive spacetime toward chaotic, mixmaster-like behavior. An ekpyrotic field moving down a steep negative potential can suppress those irregularities, making the universe flatter, smoother, and more homogeneous as it contracts, performing through slow compression some of the organizing work that inflation performs through rapid expansion. In the original brain-inspired version, developed from higher dimensional theory, our visible universe is represented as a three-dimensional brain embedded in a larger dimensional bulk, and the hot Big Bang is associated with a collision between brains. The collision is not two ordinary universes smashing together inside a pre-existing room. It is a change in the separation of higher dimensional objects whose interaction may release energy into matter and radiation on the brain, creating the hot state from which conventional cosmology proceeds. In this interpretation, time need not begin at the collision. A cold, slowly contracting phase exists before it, and the apparent beginning becomes a transition in a longer geometric history. The proposal evolved as researchers confronted difficult questions about singularities, perturbations, and the mathematical control of the collision, and contemporary ekpyrotic models include both singular and non-singular transitions rather than one universally accepted mechanism. The cyclic extension imagines an even larger rhythm. After a Big Bang-like event, the universe expands, cools, forms galaxies and stars, and eventually enters a long era dominated by dark energy. Accelerated expansion stretches space enormously, diluting matter, radiation, black holes, and large-scale irregularities across volumes far larger than any single observable region. A scalar field associated with brain separation, or an effective four-dimensional degree of freedom, slowly changes its state, bringing the accelerated phase to an end and initiating ekpyrotic contraction. The contraction smooths the surviving patch. A bounce, or brain collision, creates new matter and radiation, and another hot, expanding era begins. In the Steinhardt-Turok construction, the scale factor need not return to the same absolute value after every cycle. It can grow substantially from one cycle to the next, even while local temperature, density, and the Hubble parameter repeat a broadly cyclic pattern. This allows entropy density inside a chosen region to be diluted during the enormous expansion, while the total entropy of the entire spacetime may continue increasing. It is an ingenious response to Tolman's objection, but not a universal proof that entropy has been solved, because the answer depends on how regions are defined, how information passes through the bands, what happens to black holes, and whether the global spacetime remains physically consistent. Black holes are especially important because they carry immense gravitational entropy. In a sufficiently long dark energy era, many may evaporate through Hawking radiation, while others are pushed beyond the horizon of any patch that later contracts. Yet a complete cyclic theory must still specify how their entropy, quantum information, and residual radiation are treated without quietly discarding degrees of freedom. The transition from contraction to expansion is another narrow gate. Classical general relativity with ordinary stable matter tends to drive a contracting universe toward a singularity rather than a smooth bounce. Non-singular versions therefore invoke modified gravity, quantum corrections, or effective matter that violates the null energy condition for a controlled interval. Such ingredients can produce a bounce in equations, but they must avoid ghost instabilities, uncontrolled quantum fluctuations, and other pathologies. A model that looks smooth in a homogeneous background may fail when anisotropies and inhomogeneous perturbations are included. So the survival of structure through the bounce is one of the central tests of the entire picture. The origin of galaxies must also be explained. In some ekpyrotic models, a single scalar field produces curvature fluctuations unlike those observed, so two-field mechanisms generate entropy, or isocurvature perturbations, that are later converted into adiabatic curvature perturbations. This conversion can create nearly scale-invariant fluctuations, but it may also leave distinctive non-Gaussian correlations. Improved models can reduce these signals to levels compatible with present limits, though greater flexibility makes it harder to identify one unavoidable observational signature. Primordial gravitational waves provide another possible distinction. Simple slow-roll inflation often produces an approximately scale-invariant tensor spectrum, whose amplitude depends on its energy scale, whereas basic ekpyrotic contraction generally predicts a strongly blue tensor spectrum with extremely weak power on cosmic microwave background scales. A future detection of sufficiently strong primordial tensor modes with an inflation-like pattern would challenge many simple ekpyrotic models, while continued absence would not establish cyclic cosmology, because low-scale inflation can also produce an undetectably small signal. The phrase cyclic universe also includes a radically different proposal, Roger Penrose's conformal cyclic cosmology. In that picture, the universe does not physically contract before each new Big Bang. Each eon expands from a hot beginning into an exponentially dilute future, shaped by a positive cosmological constant. After enormous times, when massive particles in bound structures no longer provide useful standards of length and duration, the remote future may be described mainly by conformally invariant radiation and gravitational degrees of freedom. Conformal geometry preserves angles in causal structure, while allowing absolute scales to be rescaled. So the infinitely expanded future boundary of one eon can, in principle, be joined to the compressed Big Bang boundary of the next. The old universe does not collapse into the new one. Its immeasurably large future is reinterpreted, after conformal rescaling, as the next universe's extremely small beginning. This depends on strong assumptions about the ultimate fate of massive particles, black holes, and gravitational information, and the detailed crossover equations remain an active subject rather than a completed consensus. Proposed traces from a previous eon, including unusual circular or localized structures in the cosmic microwave background, have been searched for, but no claimed signature has gained broad acceptance as evidence for conformal cyclic cosmology. These models, therefore, offer three different meanings of an older universe dying. In a classical oscillation, expansion reverses into collapse. In an ekpyrotic cycle, a dark, dilute cosmos is smoothed through slow contraction and reborn through a bounce or brain event. In conformal cyclic cosmology, the endless future of one eon is geometrically identified with the beginning of another, without ordinary contraction. None is currently established as the history of nature, yet each exposes a weakness in the simple image of the Big Bang as an unquestionable first instant. They ask whether a beginning might be only local to our cosmic chapter, whether entropy can be carried, diluted, or reformulated across ages, and whether the arrow of time can remain coherent when one universe gives way to the next. If a cyclic model is correct, the world before ours may have contained galaxies, black holes, perhaps planets, and perhaps forms of complexity now erased beyond recovery. But the theory does not imply that events repeat exactly, or that familiar lives return. Quantum fluctuations and thermodynamic evolution would make each cycle distinct, even if the broad rhythm endured. What passed through the transition might be only a sparse mathematical inheritance, conserved quantities, field configurations, curvature patterns, or statistical seeds too faint to recognize. The previous cosmos would not survive as a visible ruin floating beyond our sky. It would survive, if at all, in the delicate initial conditions from which our sky was built, like the final vibration of an unheard note, becoming the first tone of a new and immeasurably long song. Perhaps the universe never began, and perhaps the deeper mistake is not imagining too much time before the Big Bang, but imagining that time must point in only one direction across the whole of reality. In one family of cosmological models, the cosmos can extend without a first moment, while the arrow that distinguishes past from future emerges locally, growing away from a special, low-complexity state in two opposite directions. To us, this sounds as if half the universe must be running backward. But no observer on either side would watch shattered glass rise from the floor, or remember tomorrow before yesterday. Each population of observers would form memories, records, stars, and irreversible processes in the direction in which entropy increases around them, and each would naturally call that direction the future. The apparent reversal exists only when the entire mathematical history is viewed from outside, as though the universe were a long valley whose slopes descend away from a central ridge in opposite compass directions. Physics makes room for this possibility because most fundamental equations do not contain the sharp temporal preference that ordinary life seems to display. Newtonian mechanics, electromagnetism, general relativity, and much of quantum theory can describe an allowed process after the sign of time is reversed, even though the macroscopic world around us is profoundly asymmetric. We remember the past rather than the future. Radiation spreads outward from sources. Heat moves from warmer bodies toward cooler ones. And eggs do not spontaneously reassemble, because the universe occupies extraordinarily special macroscopic conditions from which entropy has been rising. The second law of thermodynamics is statistical rather than a separate microscopic force. Among the many detailed arrangements compatible with a large-scale state, overwhelmingly more correspond to equilibrium or disorder than to carefully organized conditions. Yet, gravity complicates the familiar picture. A smooth distribution of matter can be close to thermal equilibrium in ordinary particle terms, while possessing extremely low gravitational entropy, because gravity later amplifies tiny irregularities into stars, galaxies, black holes, and an increasingly clumped universe. The early cosmos was hot, but its geometry was remarkably smooth, and this combination makes its low gravitational entropy one of the deepest unexplained facts in cosmology. A model with two arrows of time attempts to move that mystery away from a unique first instant. Instead of placing a special low entropy condition at the beginning and allowing entropy to increase forever afterward, it places a minimum in the middle and allows complexity to grow on both sides. The central state is not necessarily an event through which travelers could pass while watching time reverse. It may be a space-like boundary, a bounce, an almost empty de Sitter-like region, or a minimum of gravitational complexity, depending on the theory. Near it, large-scale conditions are simple. Farther away in either temporal direction, structure, records, and entropy become richer. The two halves are then not an older universe and a younger universe in the ordinary sense. They are two futures sharing a common, low-entropy origin. Although observers inhabiting either branch would describe the central region as their past. This idea appeared in different forms. Anthony Aguirre and Stephen Grattan explored a steady-state, eternal inflation construction in which a special null surface separates two inflating domains. The thermodynamic arrow points away from that surface on both sides, allowing inflationary regions and hot, Big Bang-like pockets to develop in each direction without assigning one side a universal precedence over the other. The boundary is chosen to contain little conventional matter and to possess highly ordered conditions, so it does not behave like a populated moment from which clocks can simply be carried backward. The proposal demonstrates that an inflating spacetime can be extended in a time-symmetric manner under carefully selected boundary conditions, but it does not show that such conditions arise inevitably. Questions remain about geodesic completeness, the physical interpretation of the null boundary, and whether the required low-entropy state should itself count as a beginning in a broader explanatory sense. Sean Carroll and Jennifer Chen developed a related but distinct scenario in which a nearly empty spacetime with positive vacuum energy can fluctuate into inflationary regions. In their picture, entropy has no finite maximum because gravity and inflation can continually create new regions with room for additional structure. So a generic low-density background may generate arrows of time toward both temporal infinities. From a middle region of comparatively low complexity, spontaneous inflation can occur in either direction, producing universes whose inhabitants each see an expanding, cooling cosmos behind their own forward-moving thermodynamic arrow. This framework seeks to explain why entropy was lower in what we call the past, without declaring the whole universe to have been placed in one unique initial macrostate. Yet, it depends on assumptions about vacuum stability, the measure over cosmological states, signaling, and the global behavior of spacetime. Other analyses have argued that non-singular versions may still require compact spatial sections or special conditions near the central region, while allowing singularities changes the global picture again. The phrase past eternal therefore needs precision. A coordinate may extend to negative infinity, while some physical trajectories still end after finite proper time, and a spacetime may contain no preferred first slice, while remaining geodesically incomplete for particular observers. Eternity on paper is not automatically completeness in geometry. A different route begins with the emergent universe scenario. Here, the universe approaches an Einstein static state in the infinitely remote past. Spatially closed, finite in volume, neither expanding nor contracting, and balanced by positive curvature, matter, and often a scalar field. It then leaves this nearly static condition, enters inflation, reheats, and becomes the hot, expanding universe familiar from standard cosmology. Because the static phase can extend asymptotically toward the past, there need be no finite first time, and, if its radius remains well above the Planck scale, no compulsory passage through an initial quantum gravity singularity. The elegance is quiet and immediate. Instead of exploding from a point, the cosmos waits in a timeless-looking equilibrium that is still part of time, then slowly awakens. But the Einstein static universe is famously delicate. Homogeneous perturbations can destabilize it. Quantum fluctuations may prevent it from surviving for an infinite duration. And successful models often require carefully designed matter content, modified gravity, or special scalar potentials. Some versions use the instability as the graceful mechanism that initiates inflation, while others struggle to explain why the universe remained close to equilibrium for an unlimited past before departing at all. A state that exists forever and then changes raises a probabilistic tension, because an eternally available instability would seem to have had endless opportunity to occur earlier. The answer may depend on asymptotic behavior rather than ordinary weighting, but the issue reveals how easily intuitive language fails near past infinity. Two-headed time also appears in more abstract gravitational models associated with the idea of a Janus point. In simplified, unconfined systems of gravitating particles, the overall size can reach a minimum, while a dimensionless measure of clustering or complexity grows away from that minimum in both directions. Bound subsystems, records, and local thermodynamic arrows can form on each side, even though the underlying equations remain time reversal symmetric. The central configuration acts like the two-faced Roman figure Janus, looking toward two expanding histories. These models are mathematically illuminating because they show that directed complexity can emerge without inserting a conventional one-sided beginning, but they are not full descriptions of our universe. They omit quantum fields, relativistic spacetime, cosmic expansion driven by dark energy, and much of the thermodynamic structure needed for realistic cosmology. Critics also dispute whether the apparent arrow truly avoids a special low-complexity condition or merely redescribes one. Still, the lesson survives the disagreement. A universe governed by reversible laws can contain observers who experience irreversible time in two opposite global directions. No current observation establishes that our cosmos belongs to such a structure. The cosmic microwave background reveals a smooth early state on our branch, not a second branch beyond it, and inflation can erase information about whatever preceded the hot Big Bang. Certain models might influence large-scale power, spatial curvature, primordial gravitational waves, or correlations among perturbations, but the predictions are highly dependent on how the central state and transition are constructed. The scientific value of these ideas lies less in a confirmed signal than in the conceptual pressure they place on the word before. If the universe is past eternal in an emergent phase, then before the hot Big Bang, there may have been an indefinitely old, nearly static cosmos. If time has two arrows, then beyond our low entropy boundary, there may be another expanding history whose inhabitants regard us not as their past, but as lying beyond their own beginning, in a direction they would never call future. Neither picture has one consensus, and both face serious dynamical and quantum challenges. Yet they reveal that an eternal universe need not resemble an endless chain of earlier days receding behind us. Eternity may be asymptotic, never reached by any finite clock, or divided around a quiet center from which two histories unfold. Somewhere beyond the oldest light, time may not be a single river pouring out of one spring. It may be a still watershed under a starless sky sending two rivers away from itself, each carrying galaxies, memory, and the feeling of forward motion toward a different infinity. The deepest possibility is not that another universe existed before space-time, nor that an ancient darkness waited for the Big Bang, but that the words before, existed, and waited may all lose their meaning beyond the boundary where space-time itself emerges. Every familiar description of reality assumes a stage containing distances and durations. Objects occupy positions. Fields vary from place to place. Causes precede effects, and clocks compare one physical change with another. Yet, a fundamental theory of the universe cannot quietly assume that stage if its task is to explain where the stage came from. General relativity and quantum mechanics reveal this problem from opposite directions. In ordinary quantum theory, particles and fields evolve with respect to a time parameter supplied from outside the system, as if an invisible laboratory clock were always available. In general relativity, no such external clock exists. Time is woven into the gravitational field, and the geometry that defines seconds and distances changes in response to matter and energy. When physicists attempt to quantize the entire universe, the background clock disappears, because every clock is itself part of the system being described. This tension becomes explicit in canonical quantum gravity, where Einstein's theory is rewritten as a sequence of spatial geometries related by constraints. The resulting Wheeler-DeWitt equation is often written schematically as the quantum Hamiltonian acting on the wave function of the universe equals 0. Unlike the Schrödinger equation, it contains no external time variable telling the universal wave function how to advance from one moment to the next. At first glance, the universe appears frozen, represented by a timeless quantum state containing all allowed configurations of geometry and matter at once. This does not necessarily mean that nothing happens. It may mean that change is not fundamental in the form we experience it. A clock inside the universe can be chosen from one of its own degrees of freedom, perhaps the value of a scalar field, the volume of space, or the motion of a physical subsystem, and other quantities can then be described relative to that clock. Time becomes relational, not a substance flowing behind events, but a measure of how one part of the universe changes with respect to another. The idea has roots in both general relativity and the relational philosophy of physics. Yet quantum theory makes it more subtle because the chosen clock can fluctuate, become entangled, and fail to define a single global ordering. Different internal clocks may provide descriptions that agree only approximately in simulcast regimes, raising the possibility that ordinary time is an emergent convenience rather than a unique ingredient of the deepest theory. The Page-Wouters mechanism offers one illustration. A total quantum state can remain stationary while subsystems within it display correlated sequences. An observer, using one subsystem as a clock, sees another subsystem evolve, even though the combined state possesses no external temporal motion. This framework does not by itself describe the birth of our universe, but it demonstrates how experienced change can arise from correlations inside a globally timeless structure. The distinction resembles a complete musical score lying still on a page. The score does not physically move from its first note to its last, yet relationships among the notes define an order, and a listener traveling through that order experiences rhythm and progression. In quantum cosmology, there is no listener outside the score. Observers, clocks, memories, and the very feeling of passage must all arise within the pattern. For such an internal world to appear classical, quantum alternatives must lose their ability to interfere in practice. Through decoherence, a system becomes entangled with countless environmental degrees of freedom, causing certain stable configurations to behave as though one definite history has been selected, even though the larger quantum state may retain a superposition of possibilities. Records form within these serialization branches, and those records establish an apparent past. The arrow of time may then be linked to the growth of entanglement and entropy from a special low-complexity condition rather than to a fundamental cosmic clock. Before this emergence, asking what happened first may be no more appropriate than asking which side of an uncut crystal appeared before the others. The structure may contain relations from which temporal order later becomes meaningful, without itself being arranged along an earlier timeline. Space may be equally non-fundamental. General relativity teaches that geometry is dynamical, but several approaches to quantum gravity go further and suggest that geometry is assembled from discrete or algebraic relationships that are not themselves located anywhere. In loop quantum gravity, quantum states of space can be represented by spin networks, graphs whose links and nodes carry labels associated with areas and volumes. The graph should not be imagined as a lattice floating inside a hidden room. Its connectivity helps define what spatial adjacency means. Two nodes are near because the quantum state relates them directly, not because they already occupy neighboring coordinates. Smooth three-dimensional space could arise only when vast numbers of these microscopic degrees of freedom organize into collective states, much as a continuous fluid emerges from molecules that are not themselves tiny pieces of wetness. Group field theory extends this intuition by treating elementary quantum geometric building blocks through field-theoretic methods, with some cosmological models interpreting an expanding universe as a condensate phase of many such quanta. These constructions remain theoretical, and deriving realistic space-time, matter, and observed cosmology from them is still an active challenge. But they provide a precise mathematical setting in which before space does not mean elsewhere. It means a regime where adjacency, distance, and volume have not yet taken their classical form. Causal set theory begins from a different foundation, proposing that space-time is built from discrete events connected by a partial causal order. The primitive facts are not coordinates, but relations indicating which events can influence which others. A smooth relativistic space-time would emerge statistically when the causal set becomes sufficiently large and appropriately structured. Even here, however, the word event may carry more temporal flavor than the deepest theory ultimately permits. And the central difficulty is recovering the richness and locality of four-dimensional geometry without introducing unwanted structures. String theory offers another route toward pre-geometric reality. Its extended objects and dualities suggest that different classical geometries can describe the same underlying physics. A universe that appears extremely small in one geometric description may be equivalent to a large universe in another, and topology can sometimes change without producing the catastrophic behavior expected in classical geometry. In the string-inspired pre-Big Bang scenario, a weakly coupled, low-curvature phase can evolve toward a high-curvature regime before connecting, through presently uncertain string and quantum effects to the hot, expanding universe. Yet the more radical lesson of string theory may be that space-time itself is not the primary object. The holographic principle, sharpened in gauge gravity duality, shows in certain highly structured settings that a gravitational space-time can be equivalent to a quantum theory defined in fewer dimensions without gravity. Geometric depth in the gravitational description is then encoded in patterns of quantum information in the other description. This does not provide a direct model of our cosmological beginning, because the best understood examples involve boundary conditions unlike those of the observed universe. But it demonstrates that a world containing curved space and gravity can emerge from variables that do not resemble ordinary space at all. Research connecting geometry with quantum entanglement deepens that suggestion. In holographic models, changes in entanglement structure are related to changes in spatial connectivity, and tensor network constructions offer simplified pictures in which smooth geometry resembles the large-scale organization of entangled quantum degrees of freedom. If entanglement is reduced, parts of the emergent space can effectively separate. If the pattern is rich and coherent, a connected geometry appears. Such results do not prove that our universe was created by entanglement, yet they weaken the assumption that distance must be fundamental. Before classical spacetime, reality might be best described by a quantum state, an algebra of observables, a network of causal or entanglement relations, or an object not yet captured by existing mathematics. The transition into spacetime could then resemble a phase change. Water becomes ice without any individual molecule turning into a miniature crystal, and a metal becomes magnetic when microscopic components collectively align. In the same way, no isolated pre-geometric unit would need to contain a fragment of space or a droplet of time. Geometry and temporal order could arise only through the collective behavior of an enormous quantum system. The Big Bang would mark not the explosion of matter into a prepared arena, but the formation of the arena itself as a stable macroscopic phase. Near that transition, concepts such as dimension, locality, and causal sequence might fluctuate or cease to possess definite values. Classical singularities could disappear because the variables that diverge, such as curvature at a point, would no longer be fundamental quantities in the deeper regime. Still, emergence alone does not answer every question. A timeless quantum reality must somehow produce the particular four-dimensional spacetime we observe, with its particle content, constants, low initial gravitational entropy, and nearly uniform early conditions. It must explain why locality works so accurately at accessible energies, why Lorentz symmetry is respected to extraordinary precision, and how testable traces of the transition might survive later inflation or thermal evolution. Candidate signatures could include altered primordial spectra, unusual non-Gaussian correlations, violations of standard dispersion relations, relic topological structures, or a characteristic background of gravitational waves. But no such observation has yet established a pre-geometric origin. The possibility, therefore, remains profound without being confirmed. If it is correct, there was no hidden clock measuring an age before the Big Bang, and no empty distance separating a timeless foundation from the first light. There was a deeper order in which time and space were not absent in the way objects can be absent from a room, because there was not yet a room, an interval, or a sequence in which absence could be counted. What we call the beginning may have been the moment only from within the world that emerged afterward. Beneath that moment, reality may not have been earlier, smaller, or darker. It may simply have been organized according to principles from which earlier, smaller, and darker had not yet learned how to exist. How could we ever know what came before the Big Bang when no telescope can simply turn toward an earlier sky and photograph it? When the first light we can directly receive was released hundreds of thousands of years after the hot beginning, and when any more ancient message has crossed a universe that has expanded, cooled, scattered, collapsed into structure, and perhaps erased much of its own memory? The answer is that cosmology does not search for the past as an archaeologist searches for an intact room beneath the ground. It searches for transformations that leave calculable fossils, patterns that different origin stories cannot reproduce in exactly the same way. A theory of the pre-Big Bang universe becomes scientific only when it connects its hidden stage to quantities that can be measured here: the geometry of space, the statistical distribution of primordial fluctuations, the polarization of the cosmic microwave background, the abundance of relic particles, or the frequency spectrum of gravitational waves. No single observation is likely to announce that time began, bounced, or emerged. The more realistic path is convergence, in which several independent signals gradually favor one dynamical history while closing the mathematical routes available to its rivals. The cosmic microwave background remains the cleanest surviving screen because its temperature and polarization maps preserve the initial conditions from which later structure grew. Cosmologists decompose those maps into angular scales, much as a musical chord can be separated into frequencies, and compare the resulting power spectra with equations for scalar density perturbations, tensor perturbations, spatial curvature, and the contents of the primordial plasma. The scalar spectrum already tells us that the earliest measurable irregularities were nearly, though not perfectly, scale invariant, mostly adiabatic, and close to Gaussian. These properties fit broad families of inflationary models, but they do not uniquely identify inflation, because carefully constructed bouncing or contracting scenarios can imitate portions of the same spectrum. The decisive information may lie not in the broad shape, but in its fine structure: a running spectral index, oscillations caused by a sharp transition, a cutoff on the largest scales, correlations between curvature and isocurvature modes, or a phase pattern that records how perturbations crossed a bounce. Every proposed signal must survive comparison with foreground contamination, instrumental noise, late-time gravitational lensing, and cosmic variance, the unavoidable uncertainty produced by having only one observable universe. The largest angular scales are especially frustrating because only a small number of independent modes fit inside our sky, so an apparent anomaly can remain forever suspended between new physics and statistical chance. Polarization offers a second and more delicate archive. Scalar density fluctuations mainly generate E-mode polarization, while primordial gravitational waves can generate a large-scale B-mode pattern. Detecting that pattern with the expected frequency dependence and spatial correlations would provide evidence that space-time itself carried tensor fluctuations at an early epoch. Present bicep/Keck analyses have not established a primordial signal and place a leading upper limit near r less than 0.036 for the tensor-to-scalar ratio in the standard framework, leaving many low-scale inflationary models viable while disfavoring some simpler, high-amplitude potentials. Future full-sky polarization efforts, such as LightBird, are designed to push far deeper into this territory. But even a detection would not translate automatically into inflation proved, because bounces, phase transitions, cosmic defects, and other early sources may also produce gravitational radiation with different spectra and non-Gaussian structure. The real test would be the complete fingerprint: amplitude, tilt, polarization, frequency dependence, and correlations with scalar perturbations. Gravitational waves may carry information from epochs opaque to light because, once produced, they interact extraordinarily weakly with matter. A primordial background could extend across many decades of frequency, with different instruments listening to different portions of the same ancient composition. Microwave polarization at the lowest frequencies, pulsar timing across nanohertz scales, space interferometers at millihertz frequencies, and ground-based detectors at much higher frequencies. Inflation usually predicts a comparatively gentle tensor spectrum in its simplest forms, whereas pre-Big Bang string scenarios, first-order phase transitions, cosmic strings, and some bouncing models can produce blue spectra, peaks, breaks, or bursts. Matching a signal across multiple bands could therefore reveal not only that an early process occurred, but also its energy scale and expansion history. Yet astrophysical populations of black hole and neutron star binaries create their own stochastic backgrounds, so the primordial component must be separated statistically rather than recognized by sound alone. Reviews of primordial gravitational wave searches emphasize that the scientifically useful object is not a vague ripple from the beginning, but a measured spectrum whose shape can be confronted with entire classes of early universe dynamics. The microwave background contains another archive hidden not in its map, but in its color. An ideal thermal universe produces an almost perfect blackbody spectrum, yet energy release and the damping of small-scale primordial fluctuations can create tiny spectral distortions. Those deviations could probe scales far smaller than ordinary CMB anisotropy measurements, potentially revealing enhanced primordial power, decaying particles, primordial black holes, or thermal events occurring long before recombination. Because different mechanisms deposit energy at different times, they generate different mixtures of distortion shapes, allowing the frequency spectrum to function as a blurred chronology of otherwise invisible epochs. Spectral distortion research is therefore valuable not as a solitary answer, but as part of a multi-messenger comparison with gravitational waves and 21-centimeter observations. The redshifted 21-centimeter line of neutral hydrogen may eventually provide something even more ambitious: a three-dimensional map of enormous cosmic volumes before and during the formation of the first stars. Instead of observing one two-dimensional surface, such surveys could sample many layers in redshift, greatly increasing the number of primordial modes available for statistical analysis. Their power spectra and higher-order correlations may tighten constraints on primordial non-Gaussianity, helping distinguish the simple fluctuations of single-field slow-roll inflation from additional fields, non-standard initial states, contracting phases, or interactions among heavy particles in the early universe. The challenge is immense because the faint cosmological signal lies beneath bright galactic and extragalactic radio foregrounds, and the astrophysics of heating and reionization can imitate primordial structure. But multitracer methods and improved modeling may recover information inaccessible to the microwave sky alone. Large-scale galaxy surveys add another layer by measuring baryon acoustic oscillations, redshift space distortions, weak gravitational lensing, and the scale-dependent clustering that certain forms of primordial non-Gaussianity would create. These observations can test whether the initial perturbations contained extra fields, whether gravity evolved differently after the hot Big Bang, and whether spatial curvature departs from zero. Curvature is especially relevant because some emergent, no-boundary, and tunneling models assign different probabilities to open, flat, or closed histories. Although a near-flat measurement cannot uniquely identify the mechanism that produced it, searches for circles or repeated patterns in the microwave background can also test whether space has a compact global topology smaller than the observable horizon. A positive detection would revolutionize cosmology, while a null result only pushes the characteristic scale beyond what we can presently see. Particle physics contributes from below rather than above. Accelerators, neutrino experiments, dark matter searches, and tests of fundamental symmetries constrain the fields that could have driven inflation, generated the matter-antimatter asymmetry, produced a bounce, or altered gravity at high energy. Discovering proton decay might support certain grand unified histories. Detecting additional scalar fields could reshape models of reheating. Measuring neutrino properties could strengthen or exclude mechanisms of leptogenesis. None would reveal a pre-Big Bang era by itself, but each would reduce the freedom with which cosmologists can invent the unseen past. A successful origin model must also reproduce the ordinary universe after its exotic phase. Nucleosynthesis, the neutrino background, the microwave spectrum, galaxy formation, and the observed stability of physical laws. The most dramatic theory is useless if it cannot pass quietly through these established gates. There is, however, a limit that no larger telescope can simply overcome. Inflation may have stretched earlier information beyond our horizon. Thermalization may have erased detailed initial conditions. And quantum gravity may permit several mathematically distinct descriptions that lead to nearly identical observable universes. Some questions may remain underdetermined because nature has not preserved enough accessible evidence. Science would then rank possibilities rather than name a final scene, preferring models that are internally consistent, economical in assumptions, and successful across independent data, while remaining honest about alternatives. The answer to what came before the Big Bang will therefore arrive, if it arrives at all, not as a photograph of creation, but as a tightening web of exclusions and converging traces. A primordial tensor spectrum might favor inflation. A characteristic blue gravitational wave background could point toward a pre-Big Bang or bouncing phase. Correlated oscillations and non-Gaussianity might reveal a transition through a previous era. The absence of every predicted relic could strengthen models in which classical time has no earlier extension. For now, the hierarchy of certainty remains calm and clear. The hot, dense, early universe is strongly established. An earlier inflationary-like mechanism is plausible and well-developed, but not uniquely confirmed. The region near the Planck scale remains experimentally unknown, and whether time began, bounced, extended eternally, or emerged from a timeless quantum structure is still open. We may never stand outside the universe and watch its first frame arrive, but the cosmos has placed faint impressions of its youth in every direction. And by reading those impressions together, patiently, and without forcing them to say more than they do, we may someday learn whether the darkness before the first light was another age, a quantum passage, or no time at all. The universe may not have given us a final answer, but its mystery reminds us how much remains to be discovered. I hope tonight's journey left you feeling calm, curious, and a little closer to the cosmos. Please subscribe to Sleepy Space. Thank you for being here.